Assalamualaikum and hello to everyone. For today's lesson, we will continue for part 1 of chapter 2. You can pause the video to read some of the disclaimers regarding this video presentation. On the left of the screen, written in red is the subtopic for today's lesson, and on the right is the objective for today's subtopic. Now the table shows in the video right now is a comparison between how to determine the values for specific internal energy and also specific enthalpy based on the type of substance. Okay, so for water or refrigerant R1348, we have seen in the previous subtopic 2.2 to determine the values requires the use of the property table, and for this subtopic for ideal gases we will be using equations, and these equations are with respect to its specific heat. So the question now is, what is specific heat? So the general definition is as follows. Now, in the general definition, the word energy here refers to the amount of heat which has to be added because we want to raise the temperature, and we want to raise the temperature by 1 degree. Now heat can also be removed. Okay, so when we remove heat, the temperature will be reduced. Okay, so there are two types of specific heat, which are the first one is specific heat at constant volume CV, and the second one is the specific heat at constant pressure CP. Okay, now let's look at when to use CV and when to use CP. Okay, for internal energy on the left of the screen right now, it is closely related to the specific heat CV. We can see that the general definition for CV is very much similar to the previous definition, only that it adds at the end of the sentence the type of process, which now is the constant volume process. And we can express CV by the following equation. Okay, CV equals to du over dt, which we can then cross multiply. And for your information, du here refers to the change in specific internal energy, and dt here refers to the change in temperature. Okay, next, the equation can be integrated on both sides, which we can see here gives the equation to calculate the change in specific internal energies, delta U. So the unit for this form of equation is in kilojoules per kg. We can then, like before, convert it into capital letters by multiplying it with the value for mass, and the unit is now in kilojoules. Okay, now let's look for enthalpy. For enthalpy, it is related to the specific heat Cp. Okay, so on the screen right now is the definition for Cp. It is very much similar to Cv, the definition, only that at the end of the sentence, it is now a constant pressure process. Okay, and Cp can also be expressed by the following equation, which just like before, we can see that we cross multiply and it becomes in the form of dH equals to Cp dt, where dH here refers to the change in specific enthalpy. And also, same as before, we can integrate both sides of the equation, and we can get the equation to calculate for change in specific enthalpy. For lowercase letters, unit is in kilojoules per kg, and in capital letters, unit is in kilojoules. Now, when we look at both of these equations, both of these equation is used to determine the change, whether it be in specific internal energy or specific enthalpy. But if we were to look closely, okay, at the equations, to determine the properties at a state, at one state, for u, for example, for u is simply u equals to cvt, and for h is simply h equals to cpt. Okay, next, let's look at what is the relationship between Cp, Cv, and the gas constant R for ideal gases. Now, the relationship can be seen by combining both the equation for enthalpy and the ideal gas equation. Now, by combining both of these equations, okay, and doing the required mathematical steps, as shown in the video, we can get a relationship equation between Cp, Cv, and R, which here is written in red. Now, this equation is important when we do not know the name of the gas and we have to calculate the values for Cp, Cv, or R. The next relationship between Cp and Cv is seen in the property called specific heat ratio, gamma, or we can also use the letter K, where gamma here equals to Cp over Cv. Now, if we know the name of the gas, we can read the properties, we can read the values for Cp, Cv, and gamma using table A2 in the property tables. Okay, now let's look at the first example. You can pause the video to read and understand the question properly. Okay, for step 1, please try to draw and label the schematic diagram for the question. Now, from the question, okay, we can see that there is a compression process. So in the schematic diagram, there has to be two states, state 1 and state 2, which is connected by the compression process. Okay, so for step 2, okay, we can write the required equation where we can see that we have to calculate for the specific internal energy at state 1 and also the final volume, which is the volume at state 2. Okay, now let's look at step 3, which we have to determine the required properties so that we can substitute in the equation. So for state 1, okay, to calculate for the specific internal energy at state 1 just now, we have to find for the temperature. So by using PV equals to MRT, we can calculate for T1, and then we can solve for the specific internal energy at state 1. And for state 2, from the question, we know that the internal energy after the process has increased by 100 kilojoules per kg, which means here that U2 here equals to U1 plus 100, which gives us 350.2 kilojoules per kg. Okay, now by using this value, okay, we can calculate for T2, which we can then substitute into the ideal gas equation, PV equals to MRT, and solve for V2. Okay, for step 4, since we have already solved for the question, then step 4 here is not required. Okay, now for the second example, again, you can pause the video to read and understand the question properly. So for step 1, please try to draw and label the schematic diagram. So this question also involves a process. So there has to be two states, okay, state 1 and state 2, connected by the heating process. Okay, for step 2, to find the change in internal energy, we will be using the equation in capital U, Okay, why? Okay, this is because the value for mass, okay, if we were to read the question properly, the value for mass is given. Okay, so we have to calculate in terms of capital U. Okay, but when we look at the values, okay, the name of the gas is not given, so therefore we have to calculate the value for CV. Okay, we cannot use the table to read the value for CV. We have to calculate the value for CV. Okay, so how do we find, how do we calculate for the value for CV is that we can combine, okay, we can combine both of these equations. The first one is the equation for specific heat ratio, and the second one is the equation between Cp, Cv and R. Okay, so we can combine both of these equations and we can get a new equation which we can use to calculate Cv. Okay, so for step 3, okay, to find the required properties, the first property which we have to calculate is the property for R, the gas constant. So we can calculate it using the following equation. And the value for R here is 0.3079. And for state 1 and state 2, since there is no properties which we have to find, so we have to write it down. Okay, still have to write it down. And for step 4, we can first calculate for the value for Cv, which here you can see the answer is 0.8797 kilojoules per kgK. And finally, we can calculate for the change in internal energy by substituting the values, and we can see the answer is 46.2 kilojoules. Okay, so we have come to the end of today's lesson. Okay, so if there are any questions, you can leave a comment at the related forum section. Okay, thank you for your attention and have a good day.